that I am an AI researcher in the strictest sense. And what I'm going to present to you is a collaboration with Moll, who has been organizing or has been behind this conference a lot. And it was quite interesting because while I'm in a field that, as we will see in a moment, could be considered a bit closer to human-like learning than many others, during our collaboration, it became clear how different the two fields of research actually are. But before I'm going to go into the details of this, let me give you some impressions of what is going to await you. And I'm going to show you a video of the experiment that our participants had to do and invite you to follow along with this. You'll be seeing two video clips, and then you have to decide for one or the other. Very, very simple, and you'll be informed whether your decision is correct or not. And your goal is, after some time, to figure out which decision is going to be correct. Now, mastering this is one thing, but I invite you to think for a moment how you would go about making progress in this and getting better in this. Okay, there we go. Now, the first thing you might have noticed is that the participant we videoed here was particularly successful, at least at the beginning. To show maybe some of the difficulties behind this, before I tell you all about the background, if you look very closely at the next two examples, you can see that here we have waving followed by clapping, which was actually incorrect if we clicked on video 1, followed by waving and clapping, which was incorrect by clicking on video number 2. In other words, giving different answers to the same problem still was presented as being incorrect. The reasoning behind this is that this is a probabilistic task. In other words, in a given setting or for a given pairing, you'll always only be right with a certain probability instead of with certainty. And that makes the learning process just a bit more difficult. However, if you might have missed that you've seen a couple of pairings more than once in this, it might start to show that this task, even though it's fairly simple, as we will see in a moment, is not as easy as it appears. We then had the very same task, this time with listening to audio snippets instead of watching small videos. I'll show you an example of this as well. And you might have noticed certain differences in listening to this one compared to watching the other one. For example, you might have realized that this plopping sound, at least for me that is the case, was much easier to recognize again than many of the video bits we've seen before. Now, why am I presenting two of these in two different sensory perceptions when I want to talk about comparing learning between humans and AI? The reason is that we extended this a little bit further and compared learning by a computer versus learning for a human based on different senses. Because along the way, we can examine whether we make differences in learning with different senses. And quite interestingly, the computer doesn't. Because the computer, at least as we will see in a moment, in this sense that we are going to look at now, doesn't make a difference in how the information enters its system. And so let me start off by talking about the computer side of things. Now, I like to start with this picture when talking about that. even though it does not look like I'm talking about the computer side. Once I add the second picture into this, it becomes a bit more obvious. We've seen Alan Turing, who is depicted on the right-hand side here, in the talk before. Now he's a bit older in this picture. But the point is that the area of research I'm going to talk about is actually being traced back to these two gentlemen. Pavlov on the left-hand side, I don't think needs much introduction here. And there's this nice quote that in essence states that whenever a situation is reached which we don't know what to do, we make a random choice, try something if you want, and then we see what happens. And when something negative happens, we forget about what we did. And if something positive happens, we do it again. Now, this you could put into connection with Pavlov quite easily. Maybe this is also what you decided on would be the best strategy to go forward in the tasks you've just seen. And that's one of the reasons to make it probabilistic, so that this kind of reasoning doesn't apply so easily to it. However, this goes back to Alan Turing, 1948, which I particularly like since we've just heard in the previous talk that the roots of AI research is traced back to the mid-1950s. So we can again see that Alan Turing was a bit ahead of his time, even in that area as well. Now, if we take this principle, add on a couple of decades of research, we end up here, and that is again something that we've just heard being mentioned. In 2016, a computer program was written, AlphaGo, that was able to beat the human world champion in the game of Go. Why is that so interesting? It is the one game that always was believed wasn't able to be played by a computer successfully because of the combinatorial difficulties involved in this. And yet we managed to do so. Superficially, the media could claim again that the AI has beaten the human, is more intelligent than the human. And for the one game, that is definitely true, and for many, many other games by now as well. In general, as we've just heard so well, this is not the case. The research field I'm talking about is reinforcement learning. It's one area of machine learning. If you've seen the keynote just before, we've seen within machine learning there were neural networks, and a different aspect is reinforcement learning. And here we have another nice connection going back to Pavlov, because the term reinforcement learning appeared for the first time in English language in the translation of Pavlov's work. So how does it work? We have an agent and an environment. Basically, environment would be, for example, the study we present here, and the agent is the participant. Or, as for the example I've chosen here, the agent could be a player in a board game like chess, and the environment would be all the rules of the game being played. And the important point for reinforcement learning here is the fact that these two are very, very distinct from each other, meaning the agent has no information about what's going on within the environment. So you have to imagine if this program would start to learn chess, it would start doing so without any knowledge of the rules of the game involved. And this is also true for our study later on, so that might be quite interesting to keep in mind. So what happens is the environment reports its current state to the agent, for example, the current position on the board. The agent makes a decision based on this state of an action, like the next move. And then the environment does two things. It gives a short-term feedback signal to the agent, not unlike what we've seen in the study just now, which says basically correct or wrong, with the added problem that in cases like the game of chess here, we don't know whether a certain move was particularly good or not. If we would know, the game would be solved, and we wouldn't need to have a program trained to learn it. So what we do in this case instead is usually just give no real feedback, and only once the game is decided, say, well, this game was good or bad, i.e. you've won or you've lost. And then the environment updates itself internally, reports that back to the agent, and we reiterate this loop. And what the agent wants to do is total up this feedback it gets after every move, and at the end maximize the sum, if we look at it from a mathematical point of view. So what we want to do is behave optimally in the long-term perspective. And there we struggle with two phenomena. The first one is the problem of exploration and exploitation, or the trade-off between the two. Let me give you a very concrete example here. If you have some ideas about the rules of chess, you might be able to follow along. Otherwise, it really doesn't matter as much. Important is that we have one move in here that pretty much wins the game. We have 8 moves that pretty much lose the game. In both cases, almost immediately, some of them straight away. And then we have 9 moves, and I think I missed here one even, that don't change much, and the game will go on for potentially a very long time. Now, as you can see by the numbers here, if you have no idea how the game works, choosing the one correct move here can take quite a bit of random experimentation. Now, let's assume you've chosen one of the 9 mediocre moves that just keeps the game going. And the game runs on, and eventually you win. Now you come to the same situation again, which in and of itself is already quite unlikely in such a complex game. And there we come back to the idea of long runtimes and huge computational power. But let's assume we do. Now, do you pick the same move again, knowing that then afterwards you've won the game? Or do you look for a potentially different move that might be better? And this is, in a nutshell, the problem of exploration versus exploitation, which in all of these learning problems is inherent here. And I think the numbers here show that you need to do quite a lot of exploration, of exploration to eventually reach an optimal solution that is perfect instead of just good. The other problem, quite deeply inherent in these problems, is the temporal credit assignment problem. And that is the following. Let's assume this game proceeds for a few more moves, and the computer made the move it should and wins the game. You can still ask which one of those 2 moves was the one that led to this good result. Now, in this case, it might be rather obvious that you need both of them. Now, if you would have made a different move, and the game would have gone on for a bit, and then we made some silly move and lost the game, again, the question remains, which of these moves actually got us to this bad outcome? And these 2 issues, meaning deciding between exploring different things that we know might not work out, and figuring out which one of the many steps that led to the conclusion, are the 2 inherent problems in reinforcement learning. Now, the issue was that we figured out in our collaboration in trying to compare computer learning versus humanoid learning, that these 2 issues need to be somewhat present in the task, and yet it needed to be simple enough to be also interesting for the to analyze the human learning, which is usually done on fairly simple problems. Now, no research really exists in the middle of nothing and comes out of nowhere. So the kind of tasks that we use as a blueprint have been analyzed before. Now, I'm not going to go into a lot of detail on the literature here because we don't have that much time. And the nice thing about the recording is if you're interested in the background here, you can always go back to the recording and just have a look at the papers. I just wanted to give the credit where it's due and say that there has been research before on using such sequential tasks to analyze learning. And even here, even though it's psychological research, the term reinforcement learning is being used, which again highlights some of the interdependencies between these lines of research. Another point, as I mentioned before, we wanted to compare human and artificial learning, is that there are several levels we can do this on. And one of the ones we looked at is confidence, particularly in such a probabilistic task where we're never quite sure whether we picked the right answer. Confidence can be quite interesting. On a different level, it then is interesting when we compare the senses to look at confidence we achieve through different senses. I hope you might have experienced this at the very beginning when you compared the visual and the auditory experience. And you might have noticed that for some of the visual ones, it was much harder to notice whether you've seen it twice or not. While for some of the more distinct auditory ones, it was quite a bit easier. So confidence can be a quite important thing, and there has been some study on this. And finally, the comparison across the senses on the human part. Again, very, very interesting to acknowledge that computers learn based on these states that are being reported, and these states might just be numbered. So if you have a small enough number of states, the computer just receives a number between 1 and, say, 6. While we perceive different situations with different senses and learn based on them. And in this study, we tried to isolate at least 2 of them and compare what happens there. Now, I have to mention here that the original plan was not to go with visual and auditory learning, but with haptic learning as a comparison to visual learning. The issue was COVID that made at the time experimentation in the lab unfortunately impossible. We had to move things online. And so we ended up comparing visual and auditory senses. So that's why I listed here also research on tactile learning as well. So having a look at the time, let me tell you quickly what we actually had the participants and the computer go through. We had 3 pairs of stimuli. Let's call them A, B, C, D, and E, F. I'll show you later some more examples of these. And always 2 were presented to the participant. Now we could have presented the visual ones side by side. However, we wanted to keep the comparison to the auditory study as close as possible. And since we can't play the 2 sounds simultaneously and had to play them one after the other, we did the very same thing with the visual input as well. And as I mentioned before, there is no true answer which one is better than the other, but it's probabilistic. And you can see here the probabilities. We have this A-B pairing, in which A is 80% of the time correct. So A is almost always correct, and this should be fairly easy to pick up on. Now, if you look at EF, there we have the split of 60-40, which is much closer to 50-50 and will be much harder to see. And then with the CD pairing, which is in between, with 70-30, and later on in the results, we see that some quite interesting things happen with this CD pairing in here that we might not quite expect. So what did we do? We presented 20 versions of each pairing to the participant in a pseudo-randomized order, and then checked how good the participant got at picking the right answer. And then we rated this up to 6 times, only showing the pairs that they hadn't learned yet. Now, the advantage of this is that we can measure quite well how quickly participants and the computer learn by keeping track of how often we have to show them this block of 60 trials, or up to 60 trials at least. Also, we reflected the difference in difficulty in the accuracy we measured. As you can see, for the AB pairing, you had to get at least 65% correct to be considered having learned it. And for the EF pairing, we went down to being a bit better than guessing, in essence. Now, after they've learned this, they went into the evaluation period where we tested 3 things. We tested how well they've learned the known pairs, so A, B, C, D, and EF. And then we looked at whether they went beyond this. Now, having experienced the AB pairing a lot and how clear the decision was there, we then showed them A and B paired up with all the other ones. So A compared with C, D, E, F, and B compared with C, D, E, F. The idea being that A is always correct and B is always wrong. So on top of learning the exact pairings, participants needed or were hoped to learn some kind of hierarchy between the 6 stimuli. And just to give you another example, now all side by side, this is basically the collection of potential stimuli we had for the visual task. Given that I can't show all the auditory ones on the same slide, I decided to not do that. That would take too much time. But just to compare, we had, for example, if you compare those 4 here, you can see we had waving clockwise or anti-clockwise with either the right or left hand, which are all kind of similar in motion. Others were maybe a little bit more distinct. So what were our assumptions going in, both in comparing the human learning and the artificial learning? And by the way, in case you're interested in that, for the artificial learning, we used a Q-learning approach, which is a very, very well-established and fundamental approach in reinforcement learning, which is suitable for smaller tasks. So we assumed from the beginning the computer would need more training iterations, which is almost always the case in pretty much everything we know. And this was indeed the case. We also assumed that the computer would eventually achieve high accuracy because the whole setting of probabilistic tasks is not that easy for us to learn. And if we look at the results here, we can see with a small exception at the AC pairing, and well, this might not be even significant here in the BD pairing, overall, the computer did better. We can also see, and this is quite interesting here, that the rough pattern of accuracy was quite similar. We have the same kind of dips and we have the same kind of higher plateaus in the computer and the human learning. Finally, we would have assumed that human confidence would decrease with increasing difficulty. That was actually not quite the case. And this is now averaged across the different senses. We measured confidence in response time, saying that if you're not sure what you're doing, you need longer to decide what you want. And here we can see, and this is what I mentioned earlier, that the CD pairing, even though it's not the hardest one, took the longest time. And this is a point, again, I will come back at the very end of this, because we do have a theory what might be behind this. So this turned out actually to not be the case. And we also assumed that the computer's confidence would vary between different pairs, given that, strictly speaking, it should. The computer or everyone should be more certain in the AB comparison than on the EF comparison. And the CD comparison should be in between. And we found out this is actually not quite the case. Now, I don't have the time to go into the technical details of this, but we basically, Q tables is the knowledge representation within the algorithm. And based on these values, we can somehow derive how confident the computer is of making one decision over another one. And we can see here that for A, B, and CD, it's pretty much the same. And even though the gap to EF looks big, if you look at the scale, it's just from 80 down to 78. It's not that big. So actually, the computer was pretty certain or equally sure across all the different pairs. Now, as for the inner human comparison, so to speak, between sight and hearing, which we could use the computer as a baseline for, the first thing we thought there would be a difference between them in speed. And if you look at this, at first sight, it looks like that learning speed in terms of number of blocks required is different, but it turns out this difference is not significant. So actually, they needed about the same number of blocks for learning the task by sight or by hearing. Now, if you look into accuracy, we can again see that CD kind of falls out of this, at least in the audio case. We can also see that it slightly falls off with difficulty in the vision case, which is exactly what we would have expected overall. And we can see that this dip we've seen earlier is actually due to the audio channel. But, so we see in the CD case, there's a significant difference in accuracy. If we average them out, though, across all the pairs, we can again find that this accuracy stops being significant, the difference in here. And finally, the confidence. And this is quite interesting, given what we've just seen about the accuracy. We can see that the answer in the audio case was much faster than in the visual case, with the exception of this. If we look at the CD pairing again, we can see that here in the vision case, the answer took longer in this CD pairing. So we see that this falls always out of what we would expect. And as I said, I'll get to this in just a second. While if we compare familiar to new pairings, we can see the increase in response time we would expect with a lack of confidence, which in some sense also validates that we approximate confidence with this response time measurement. So this is indeed different. Now, unfortunately, I'm running out of time here. So let me quickly emphasize one thing. Well, first of all, we're playing with the idea of adding senses to the artificial agent. We've just heard that artificial intelligence algorithms or techniques are quite good when it comes to visual tasks or sometimes even text-based tasks or audio tasks. So we could add these on top of the existing algorithm to give the agent a sense of senses and get a more finer comparison between the two. We also want to include more humanoid senses as well. At latest, when we come back to the lab again, this is going to be added in. And finally, the randomized stimuli is what I've been hinting at the entire time, because our theory is that this CD comparison that turned out to be so different than we expected comes down to an unfortunate choice of the two stimuli that might have been very difficult to distinguish, because what we didn't do is randomize the stimuli that we selected for the different letters. And with this, we hope to get closer to understanding how the different types of learning compare, which can have benefits in both directions. It can both inspire us when we're looking for new and different algorithms in the machine learning context, as well as start to build bridges between human and machine cooperations when we get to that. And with that, I thank you for your attention, and I'm happy to answer questions that are coming up. And as far as I know, Merle tried to join us as well, if possible, for this.
Thank you, Maximilian, first of all, for that great talk. I think it's very interesting to compare the different learning, with confidence, and like the way you showed it was quite interesting. I would just pass on to you with a question that appeared in the chat. So someone asked, once an AI system learns to play a game well, can we learn from it in some meaningful, smart tactics to play the game better ourselves?
This is in fact what happened in a large variety of games. So the first game that caught a lot of attention when it was solved with basically reinforcement learning, and which led to a massive increase in interest in the research in reinforcement learning, was in 1995, backgammon, actually. And it's quite interesting because backgammon is a random game. You're throwing dice in the game. And I, at the time, wasn't aware, actually, that there is literature on how to play backgammon well. There is. And it turns out that watching the computer play backgammon, again, be on a human worldwide level, that a lot of typical strategies were rewritten. Books were basically falsified and rethought and rewritten because the computer found ways to play this that were not thought of before. And if we now look into more recent times, Go and chess, also there, the way the computer is playing has impact. So, for example, the computer is quite often used as ground truth, more or less, to assess certain situations and to basically know what should be the correct answer, or at least how good the two players are in comparison to each other. And for example, in Go, there's this nice quote that the player at the time who played the computer in 2016 said that the computer does not play human-like. But that he could, in essence, it would have failed the Turing test in this case, if you go back to that, because the player could tell from the playing style that there was not a human playing. But yes, we can learn a lot in these games. The difficulty is now making the transition to something more significant than games.